Okay, hey there everybody, welcome back. So in this installment of our video series on introductory econometrics, we are going to be learning about hypothesis testing and statistical inference. Now, specific subtopics that we'll be covering can be found over here. So let's hop right into that. So what is hypothesis testing? Well, it's a formalized way of coming to know something, right? So we're going to create structure and definition around how we know a thing is this, okay? We could also express this as a method of finding out what we don't know. In fact, that's maybe a little better, right? Now, around this idea of developing a method of knowing, right, there's a bunch of structure that we're going to construct and a lot of terminology associated with that. Now, all the terminology that we are going to use in this is pretty standard to scientific hypothesis testing in general. It's certainly applicable to not just economics and econometrics, but to a variety of fields. Okay, so let's get started. The first thing we want to become familiar with is this idea of the null hypothesis. And what the null hypothesis is a statement of the values that the researcher does not expect, right? So this is what we don't expect to be the case, the null hypothesis. So for example, we write that as H sub 0. H sub 0, the null hypothesis, in this case, it's going to be that beta, where beta is the estimated value of our coefficients, so we're doing econometrics here, is going to be greater than or equal to 0. In other words, we're saying we do not expect that value of beta to be equal or less than 0. All right, besides the null hypothesis, we also have the alternative hypothesis, okay? And this is a statement of what the researcher expects. So null hypothesis, what we don't expect. Alternative hypothesis, what we do expect. Okay, so example, H sub A, beta is greater than 0. We expect the value of beta to be greater than 0. Positive correlation, as I said a moment ago, okay? Now, we're going to talk about this more in just a little bit later on in this lecture, but these examples are what we call a one-sided test. And the reason why they're one-sided tests is because essentially there's the null hypothesis only sits on one side, right? So anything greater than 0 is accepted, and anything equal to or less than 0 is the null, right? So sort of it's a zone here of yes and a zone here of no, and sort of stretch off infinitely. But of course, we could certainly have hypotheses where we have a range and yes and then no, and we'll come back to that in just a little while. So one-sided versus two-sided tests, keep that idea in mind as we go forward. So here, example of a two-sided test, we're going to say that the null hypothesis beta is equal to 0, right? So now we're going to say we do not think that the value of our estimated coefficient is 0. We think that it's not equal to 0. So our alternative hypothesis, beta, is not equal to 0. Okay, this is now a two-sided situation, a two-sided test. So we've got a null that is a single point, or actually it's just a single value 0, right? And then everything else is alternative hypothesis in both directions. All right, next piece of terminology that we need to get familiar with are so-called type 1 and type 2 errors. Okay, type 1 errors are where we reject a true null hypothesis. Okay, that is, we think we are right about something, but we're not. Okay, and this happens, right? This happens a lot. We think we know something, but in fact we don't. Similarly, we can run across type 2 errors, or we can encounter type 2 errors, where we do not reject a false null hypothesis. That is to say, we think we are wrong, but it turns out that we're right. Okay, now the thing about type 1 and type 2 errors is anything we do to reduce type 1 type errors in our hypothesis testing is going to increase the likelihood of type 2 errors. And anything we do to reduce type 2 errors is going to increase our likelihood of getting type 1 error types. So there's no right answer as to how to fully safeguard against type 1 versus type 2 answers. It's a matter of application. Different types of hypothesis tests. One should be consulting the literature about safeguards against type 1 and type 2 errors. Next piece of terminology, a decision rule. Okay, what is a decision rule? Well, decision rule is a method the researcher may develop and utilize to determine when to reject the null hypothesis. In other words, we're going to say, if this thing occurs, or if we find this thing, then we will reject the null hypothesis. Now, decision rules generally utilize a range of possible values of beta in econometrics, right? That will be accepted as consistent with the hypothesis and a range that will be rejected relative to the null hypothesis. A so-called critical value, another piece of terminology, defines these two ranges, right? So we're going to essentially say, well, we're going to develop a rule that says, if our ranges of beta lie within this range, we will accept. If not, we will reject. Right. Now that we've got the terminology out of the way, well, we've still got some more terminology, right? But sort of to the next level now. Okay. So a cornerstone of hypothesis testing and gauging statistical significance is this idea of the T-test. Okay. Now the T-test here, as we see, right, is the ratio of the difference between the estimated value of a parameter from its hypothesized value to the standard error, or as we see in the equation here. Okay, so I'll say that again. The ratio of the difference between the estimated value of a parameter from its hypothesized value, okay, so that chunk, estimated value of a parameter from its hypothesized, we see in the numerator here of this equation, right? So using the mouse, if you'll excuse me for a minute, right? Here, the estimated value of a given parameter, beta hat, the value of beta associated with the null hypothesis, H0, that difference over the standard error, SE, standard error, associated with the estimated value of this coefficient, K. Okay. This is the T. Okay. So we've written this as betas, right? Because in econometrics, we most often use Ttest to test hypotheses about individual slope coefficients, right? So we're looking into really the meaningfulness of these slope coefficients. Okay, so now let's bring some of those ideas about decision rules into our idea of T-tests, which we've just discussed. T-tests give us a method for deciding whether to reject a null hypothesis. In other words, T-tests can form the basis for decision rules. Okay, we call the t-values that define our acceptance range, right? So remember that decision rule, we're going to define a range, right? We define our acceptance hypothesis as the critical t-values. Okay, so the critical t-values is going to define the range, which in turn defines our decision rule about whether we're accepting or rejecting the null hypothesis. Okay. Now, there is no correct range of acceptance. The matter is subjective. Okay, but we need to document what we're doing. We're going to document what's going to be called the level of significance, which will get you in just a few minutes. Assumptions of the t-test, right? We are assuming that we have normal distributions, okay? And based upon what we said about null and alternative hypotheses, the nature of those, we need to determine whether the appropriate t-test is a one-sided or a two-sided test, okay? And again, the appropriateness of one-sided versus two-sided tests comes by the construction of the null and alternative hypotheses, okay? All right. Now on this, in another video, I'm going to show you, we're actually going to do a t-test, right? And we're going to show what it looks like in the regression output. and we'll talk about its sort of applied meaning there. This is essentially going to be sort of our theoretical statement here. All right, so now our t-test, right, is like a lot of our other tests and statistics associated with our regression output. It's easy to overstate or to misapply the meaning and implications of the t-test. T-tests that suggest statistical significance, okay, do not necessarily reflect causal or even correct relationships between the independent and dependent variables. So just because the t-test associated with a given estimated value of beta suggests statistical significance, it doesn't necessarily mean that our estimated regression equation is consistent with our causal hypothesis, nor is it even the case that we necessarily have the correct relationship between that independent variable and our dependent variable. Because at all times we always have the possibility of spurious correlation. In other words, it may be the case that these two variables happen to move together often, but that there's no causal relationship or even meaningful correlation between the two. Similarly, we should not be using the t-test to rate the importance of variables. So in our regression output, we're going to find the different coefficients, different estimated betas, are going to have different t-statistics associated with them. Just because a variable has a higher t-stat than another t-stat does not mean that it's a better or even more important variable. Okay? Instead, what t-tests do is they give us an indicator of how meaningful that coefficient associated with the given independent variable is in explaining variations in the dependent variable. Okay? So we think about a given variable, x, x1, x2, whatever, right? We have a coefficient associated with that value of x in our regression output. Okay, the t-stat is giving us an indicator about the quality of that coefficient. In other words, it's not giving us a notion of the quality of the variable itself. It's giving us an idea about the quality of the coefficient associated with that variable. In other words, the quality of how movements in the independent variable correlate with movements in the dependent variable. Okay. Finally, t-tests tell us something about the quality of the sample, right? So, which makes sense given what we just said, right? In this case, the t-test associated with a given independent variable is telling us something about the quality of the sampling of that variable, right? So in this case, the t-test for this x variable, for x1, the t-test associated with the beta value, the estimated beta value coefficient on this variable, is telling us something about the sampling of that variable, right? About the quality of the sampling of that variable, not about the nature of the variable itself. Okay. Next thing, confidence intervals. Okay. Now all these things are related, of course, right? Confidence intervals are a range of values that will contain the true value of beta a given percentage of time. Okay. Here we see sort of a normal confidence interval table, right? The 1, 2, and 3 there refer to standard deviations. You'll probably remember from your introductory statistics, right? So, a confidence interval in our applications looks like this. Okay, over here we see essentially the construction of the confidence interval in the type of situations that we are trying to understand here. So, the estimated value of the coefficient beta hat plus or minus a two-sided confidence interval, whichever one we're choosing, right? So we've got three here, 68%, 95, 90, 99% confidence interval. Two-sided, plus or minus a two-sided confidence interval times the standard error associated with the estimated coefficient, beta hat. This is how we constructed constant confidence interval. Okay. All right, finally then, the idea of the Ftest. Okay, so Ftest is not a specific type of test, but rather is a category of statistical test in which the test statistic has an F distribution under the null hypothesis. All right, now that's kind of fancy, and we really only need to understand the specific type of Ftest that we are running here. Okay, and what the Ftest tells us is it gives us a method for rejecting the estimated regression equation out of hand, right? So should we reject the entire estimated regression equation, okay, Ftest? We construct the Ftest this way, okay, where all of our variables here stand for the things they have before. So RSS, residual sum of squares, and number of variables, okay, so on and so forth. The only new variable we have in this equation that we've not seen before is this m, which is the number of constraints that we place on this equation. Now, we'll talk about that a little more in a future video. For right now, we can kind of leave it there. We're going to use the Ftest to reject the null hypothesis if our F value ends up being greater than the critical value of F. Okay, and that critical value, like with Ttest, is going to depend upon, you know, a lot of the things in this equation: number of variables, number of observations, so on and so forth. Okay. Now, the null hypothesis H0 in this Ftest, so in the Ftest that we're running for our estimated regression output, is the possibility that all of our betas, so all of our estimated coefficients, are all simultaneously 0. Now, a very plain way of saying this is to say that our entire hypothesized relationship, our alternative hypothesis about sort of what we think these relationships are, is wrong. Put another way, this is a test to determine if the fit of our estimated equation is no better than using the mean value of the dependent variable. So going back to our, way back to chapter 1, chapter 2, when we did this height and weight thing, right? We hypothesized that a person's height could be essentially forecast from their weight, right? Or that we could predict somebody's height based upon their weight. The null hypothesis here would be that just simply taking the mean value of all observed heights is just as good as our hypothesis that we can determine height from weight. In other words, say another thing, that our estimated relationship here between these independent and dependent variables does nothing, right? This is what the Ftest is telling us, okay? All right. In the companion video to this, I'll be walking I'll walk you through all this using some actual regression output. I hope to see you there. All right. See you next time. Bye.